Hello, I am Lin Yi, and together with me are Trisha and Zer Jynn. We will be presenting our research on math modeling of population growth across nations. I'll give a brief introduction on our project before we dive deeper into its research and content. Research has shown that logistic growth patterns have been proven to be true in various organism populations in both controlled and natural environments. For example, yeast grown in ideal conditions in a test tube showed the classic S-shaped logistic growth curve, whereas the recorded natural population of harbor seals shows a real-world fluctuation. However, it is still oscillating around its carrying capacity, confirming this logistic pattern. A simple way to explain this would be that as the population grows, the resources needed for survival would soon deplete. As such, the population may exceed its carrying capacity before falling and remaining stagnant. The carrying capacity refers to a species' average maximum population size in a particular habitat. This goes the same for human population growth. In many developing countries, lack of land space is a growing issue, especially with their rapidly increasing population. Additionally, there are limited food sources to provide to the populations, which may lead to a lack of sufficient food for everyone. Moreover, developing countries used to be known for their high birth rates. This is due to a few factors, such as the need for children to work to earn income for the family, lack of education and knowledge of family planning, as well as high infant mortality rates. More often than not, families living in developing countries tend to have more children in hopes that some would survive. This brings us to the aim of our project, which is to investigate the population trends in some of the largest countries in the world and further investigate how the decreasing birth rates affect the population growth in some countries.
In our analysis, the main contributing factors and variables taken into consideration are the birth rate per 1,000 people, death rate per 1,000 people, total fertility rate, and time. These are our assumptions. First, we are assuming that the total population is primarily affected by the birth and death rate. Secondly, we assume that the external factors, such as migration, are negligible from the models we use. Thirdly, that the amount of land space does not affect the population growth. And lastly, that the death rate will reach a minimum of 3 deaths per 1,000 people.
After we've made our assumptions, we moved on to our preliminary analysis. After our preliminary research, which included the analysis of 30 countries, we found that most countries could be represented by a quadratic curve, for example, Kenya. However, we further analyzed the population trends of 4 countries which are better represented by an exponential curve. These countries are Pakistan, Nigeria, Democratic Republic of Congo, and Tanzania. Next, let's move on to our hypothesis. We hypothesized that the population growth will result in an S-shaped curve or logistic growth trend in the long run, as the country becomes more developed and the finite resources available in the country depletes. The logistic function means that the rate of growth will be exponential at first, but slows down to a plateau. From 1960 to 2018, the birth rates in both developed and developing countries have been decreasing, and it is assumed that it will continue to decrease following the respective graph trends. With the decreasing birth rates and limited amount of resources available in these countries, the population will start to decrease. It is hypothesized that the population growth will result in an S-shaped curve or a logistic growth trend. Figure 31 shows a comparison between an exponential and logistic growth curve. The logistic growth model is a certain differential equation that describes how a quantity might grow quickly at first and then level off. This means that the growth rate would be exponential in the first X years, but slow down, coming to a plateau, and form an S-shaped curve. The carrying capacity, K, where the graph flattens, is a species' average maximum population size in a particular habitat. The population size is limited by the environmental factors like adequate land, food, shelter, water, and mates. If these needs are not met, the population will decrease until the resource rebounds, hence putting a limit on the growth. Here is a logistic function growth curve. It models the exponential growth of a population but takes into account the carrying capacity of the environment. Now, let's look at the difference between the two graphs. An exponential graph has a gradient that always increases and the growth does not slow down, and it has an infinite y value. A logistic graph, however, has an increasing gradient until it reaches the carrying capacity of the environment, and it will decrease in y value at an increasing rate. The y value stops decreasing at the carrying capacity k. Here is our model equation for the logistic function graph. Y is the population size as a function of time t. K is the horizontal asymptote or carrying capacity of the population and determines the maximum y value of the graph. B is the constant that helps to control where the curve crosses the y-axis and determines the y-intercept. P is the parameter which affects the rate of exponential growth. X is the flexible horizontal translation of the logistic function. Finally, C represents the y value at which the graph starts when x equals to 0.
Using the extrapolated birth and death rate graphs, we found out that for Pakistan, the birth rate is equal to the death rate at a value of around 7.6 when y is equal to 2041. We then calculated the country's total population and plotted the graph of population growth to find the total population in 2041. We used the same method to find Nigeria's total population in 2081, where the birth rate and death rate were equal at about 3.2. For the Democratic Republic of Congo, it is predicted that their population will reach its maximum value in the year 2119, with its birth rate and death rates at around 2.9. Tanzania's population is expected to reach its maximum in the year 2108, with its birth and death rates equal at around 3.0. In our equation, K directly determines the carrying capacity. The maximum carrying capacity is equal to the value of the sum of K and C. When K is greater, the horizontal asymptote is also greater. This is illustrated by the two graphs on the right side, showing the comparison between a graph with a K value of 1 and the other with a K value of 2. In this case, since the C value is 0, the maximum Y values of the graph are 1 and 2 respectively. The B value determines the steepness of the graph. A larger B value would result in a longer amount of time taken to reach the carrying capacity. As shown on the right, a graph with a B value of 5 will have a significantly lower growth rate than the one with a B value of 1. Similarly to the B value, the P value affects the growth rate of the graph. A greater P value would result in a higher population growth rate. As illustrated in the image, a graph with a p-value of 5 will have a steeper gradient as compared to the one with a p-value of 1. This will allow the population to reach its maximum carrying capacity at a faster rate. The c-value affects the y-value at which the graph starts. A higher c-value would mean that the graph is slightly elevated and does not start from the x-axis. From this illustration, we can see that the purple graph, which has a c-value of 3, starts at a higher y-value. However, we can observe that both graphs reach their maximum carrying capacity at around the same time. Hence, it can be concluded that the c-value of the function does not affect the population growth greatly. As shown in the graph above, DR Congo has the largest carrying capacity. However, it was noted that the country reaches zero population growth at around the same time as Tanzania, which has a carrying capacity nearly 3 times smaller. The reason for DR Congo's rapid population growth is due to its growth rate, which is controlled by the coefficient of E, or the value of B. DR Congo has a higher B value of 210, which allows it to achieve a larger maximum population as compared to Tanzania, with a B value of 96. Similarly, comparing Pakistan with Tanzania, both have a very similar K value, or the carrying capacity. However, the main differentiating factors between their graphs are the B and C values. Pakistan, which had an initial Y value of 45 when x is equal to 0, theoretically needed a shorter period of time to reach its maximum population size of 263 million. On the other hand, Tanzania, which had a lower Y value of 10 when x is equal to 0, took a longer time to reach its maximum population size of 288 million. Moreover, Pakistan had a smaller B value of 31 as compared to a value of 96 for Tanzania's graph. This allowed Pakistan to reach its maximum carrying capacity much faster than Tanzania. When the graphs for Nigeria and Pakistan are compared, it is noted that both have the same C value of 45, and this means that the C value does not affect the growth rate when these two countries are compared. With a higher P value of 0.08, Pakistan's growth rate is significantly larger than Nigeria, which has a P value of 0.054. Pakistan also had a lower B value than Nigeria, and these two factors allowed Pakistan to reach its inflection point much faster than Nigeria. Early on, we noted that out of the four countries, DR Congo and Tanzania were one of the least developed countries, and all of them were lower income countries. Based on the results above, the two least developed countries had the exact P value. The main difference in the shapes of their graphs was caused by the V value, which affects the graph significantly. Hence, it is concluded that the variables which have the greatest impact on the shape of the graph are the B and P values of the function.
In summary, we explored the two main factors that affect population growth, which are the birth and death rates. We also obtained past data and used the trend line to continue plotting the graph, allowing us to calculate the population in each following year. In doing so, we discovered that all four of our population graphs follow the logistic growth trend, hence proving our hypothesis. The significance of the population projections is that population projections are used by government policy makers and planners all around the world to gauge future demand for food, water, energy, and services, as well as to forecast future demographic characteristics. These population projections can alert policymakers to major trends that may affect economic development and help policymakers craft policies that can be adapted for various projection scenarios. Logistic functions take into account the various factors that would affect a population's growth, hence allowing them to make a realistic projection of the population size in the future. Limitations and areas for future study. In order to simplify our problem, we only analyzed the birth rates and death rates of each country and did not take other factors into account. These include availability of resources and services and land size. In the future, we could build on the current foundation that we have and investigate the relationship between these factors and the growth rate of a population. We also extracted the data from only one source, which may or may not be inaccurate representation of the population. Thank you!